Good morning, everyone. Welcome to the Moment to Transfer class. So far we have discussed about Rayleigh's method and then Buckingham Pi method for determining the relationship between the variables that are available. So today we'll discuss about a model analysis or similarities. Right. First, let me tell you what is a model. So, a model is a replica of the actual structure, right? And we original mission or structure is called as the prototype. We usually consider this model and prototype because we cannot invest a lot of money on the original prototype such that if it fails, right, we'll be losing all that amount of money. So most of the cases what they do is they build a model which is similar to the prototype or the original mission, and then they test the things whether it's in reactions or whether it's a fluid flow or a heat flow or material balance or mass transfer, whatever it is, they test on that simple model to know what is happening or how it is behaving and what kind of stresses or what kind of factors that are coming into play they will be observing, and then based on the observations they build they modify the model, and then until they get success, and then they will be building the original prototype. So based on this we need to have some common similarities between model and prototype. As I said, model is a small scale replica of the actual structure, and the original structure is called as the prototype. What kind of similarities you should have when you build a model and a prototype? Right? There are three kinds of similarities that you need to maintain to build a model on the prototype. Right? The three similarities are: the first one is the geometric similarity, the second one is the kinematic similarity, and the third one is the dynamic similarity. Right? So geometric similarity is nothing but it is the ratio of the lengths of the model and the prototype, or the diameters of the model and the prototype. That ratio should be constant. That is what it tells. The geometric similarity is about the lengths and diameters. So length of the prototype to the length of the model, that ratio should be a constant value. Likewise, the breadth, the diameters, that ratio of that model and the prototype should be a constant value. That is called as scale down or scale up. Whatever we have the terminologies, we will be using that. Suppose if you want to find this area of the prototype versus area of the model, then area of the prototype is length into breadth. If it is a rectangular cross section, length into breadth of the prototype by length into model into breadth of the model. This LP by LM is LR, BP by BM is LR again, so it is LR square, that is length of the ratios square. Likewise, volume also will be getting dP by dm whole cube or LR whole cube. That is how we will be maintaining the ratios. Right? Suppose if you have 10 meters of length of original mission, right? So and you are maintaining 10 centimeters of the length of model, then what is the ratio? 10 centimeters by 10 centimeters, it is 0.1 meters by 10, so it becomes 0.01 is the scalar ratio. Then the diameter ratio should be also in that only 0.01 ratio only, it should be there. That is the condition for the model to be built for a particular prototype. Similarly, not only geometric similarity, we also need to maintain the kinematic similarity. So kinematic similarity is nothing but the velocities ratios. That is velocity of the prototype to the velocity of the model. So the thing here is velocity of the prototype to the velocity of the model at a particular point. That is very important, at the inlet conditions or at the middle of the sections or at the outlet conditions. That ratio should be common, not everywhere. See, suppose if you take the ratios, that is where velocity of the prototype to the velocity of the model at inlet, that ratio must be equal to velocity of the prototype to the velocity of the model at the outlet, that ratio, right? That ratio should be equal, that is given as VR, velocity ratio, right? So that kind of kinematic similarity also need to be maintained for this particular cases. And the third condition to maintain is the dynamic similarity. So dynamic similarity is nothing but it is the ratios of forces. So Fi, if you take inertial forces, viscous forces, gravitational forces, whatever it is, suppose if I consider the inertial forces of the prototype to the inertial forces of the model must be equal to viscous forces of the prototype to the viscous forces of the model, right, must be equal to gravitational forces of the prototype to the gravitational forces of the model is equal to a constant value that is called as the force ratio. So this kind of ratios must be maintained to test what is happening in the actual prototype, right? So whenever we build a model, right, we should maintain these three similarities, that is geometric similarity, kinematic similarity and dynamic similarity, such that we can test it and it resembles the actual prototype, right? So this is about the similarities that need to be maintained for a particular model and prototype. And then what will be the type of forces acting on a moving fluid? You all know this: inertial forces, gravitational forces, surface tension, viscous forces, pressure force and elastic force. All these things we generally deal with the first five, the sixth one we don't deal with. The first five are important for us, right? So inertial forces, viscous forces, gravitational forces, pressure forces, surface tension forces, right? These are all important as we deal with the course, right? Then there are other dimensionless numbers that we often use in momentum transfers, like Reynolds number. You all know what is Reynolds number. So Reynolds number is dV rho by mu, right? That is what we generally use, but it is defined as the ratio of inertial forces to the viscous forces of the fluid, right? It is the ratios of forces, right? So that is important. So it is the ratio of inertial forces of the flowing fluid to the viscous forces of the fluid, right? That is important. So inertial forces is nothing but rho a v square, and viscous forces is nothing but v into a by l, right? So when you take that ratios, you will be getting dv rho by mu or lv rho by mu, whatever it is. So it is dimensionless number. And then the other forces, the other dimensional numbers also you can go through. This is the Faraday number. That Faraday number is the ratio of inertial forces to the gravitational forces. This is gravitational forces, right? And it's root over. That is important, root over, right? And then Euler's number, we know it is the ratio of inertial forces to the pressure forces. It is square root of inertial forces to the pressure forces. And Weber's number, it is the inertial forces to the surface tension forces. Again, it is root over, right? And Mach number, that we use it in compressible fluids. So Mach number, it is the ratio of square root of inertial forces to the elastic forces, right? So that is these definitions are important when you go for an GATE or such kind of competitive examinations. They will be asking you, right? So this is for now. So we have dealt with, in the last 3 classes we have dealt with units and dimensions and how they are important, Rayleigh's method, Buckingham Pi method, and then the similarities that we need to maintain, and then finally the dimensionless numbers which we use commonly, right? Thank you. We will meet in the next class.